Survives here, and today I'll be going through this problem on p-brane actions. Namely, we'll be showing that the Polyakov action for the p-brane is equivalent to the Nambu-Goto action, provided that we make a smart choice of the cosmological constant here. So one thing to note is that this cosmological constant depends on the dimension that we're working in. So this is for p-brane. A p-brane is p plus 1 dimensional. So is p plus 1 dimensional. So for example, if you have a string, then you're talking the string would trace out a two-dimensional row sheet. So p equals to 1 is the case for string theory for strings. And additionally, there's a we know from string theory that the Polyakov action is equivalent to the Nambu-Goto action without this thingy. So for p equals to 1, we kind of expect lambda p equals to 0. So namely lambda 1 is equals to 0 for strings. But for higher dimensional objects, for higher dimensional p-branes, this is not the case. It might not be 0. And in this video, we'll find out what this cosmological constant is. And yeah, let's go ahead. So, okay, let's go ahead and solve this. So they give us a hint, which is that we need to solve the equations for motion for the intrinsic metric h. So, okay, so we see a quantity which is square root of minus h over here. So what is that? H is defined to be the determinant of h alpha beta, like that. So yeah, so the first step to do the first thing we need to do is to vary the Polyakov action in order to solve for the equations of motion of the intrinsic metric. So how we do that? We vary the action with variational calculus. So we're going to vary this entire thing inside all the h's. And the derivatives, the x's, they do not change with h, so they remain constant. And then we have the other one over here. Okay, so how do we need to compute these objects, we need to compute these things. So well, we see that we can just use the product rule in a sense. And one thing that we need to calculate is the variation of h. So one can show, which I will not show in this video, but one can show that the variation of h is equals to minus h alpha beta delta h alpha beta. So this is something that we take for granted. So I'll not show that. I'll not show this in the video, but you can work through some tedious, it takes 1 or 2 lines, I believe. And so from this we can take the variation with minus h, and that we use chain rule to give us 1 over 2 minus h, and then the variation of h, right? So this variation of h is going to be, substitute this in, so we have minus h alpha beta, and from this we can get minus 1 over 2 square of minus h alpha beta alpha beta. So this is the variation of minus square root h. So this is a good result, and we substitute this into here. So let's go ahead and do the substitution. So this is product rule, and then we do, okay, I have a bit of trouble with the summation indices over here, so I'm going to relabel, because this is just Einstein's summation convention. I'm going to relabel it gamma and delta, gamma and delta, so just to make sure there's no conflict. And then product rule, so that will be plus Okay, so that is for the first term, and then for the second term is just this thing directly. Okay, so alright, so from here we can do some grouping of the terms, namely let's pull out the integral dp tau d, this one, and then there's some common terms over here. So what are the common terms? It is, there's a minus h, minus square root h, square root minus h everywhere, and there's also a variation with respect to the metric everywhere. So let's go ahead and factorize all those out. So we get square root minus h, and then we get the rest of the terms. So the first term is going to be minus tp over 2 okay, so this is minus tp over 2 minus half and then we have minus tp over 2 and then from the bottom we have minus lambda t over 2 oh, over here the indices I need to be careful. It's supposed to be, because I relabeled the indices to alpha and beta, so they should be alpha and beta. Okay, so this term, so yeah, sure enough, that gives us the equation of motion already, because this term over here is going to be 0, because with respect to arbitrary variations of the metric, in order to keep the action stationary, the only way is to this one equals to 0. Yeah, so that's our answer for the, so now we can write the equation of motion for the metric. Yeah, so for the metric, let's stare at this for a while. Okay, there's I'll just write it out. So minus tp over 2 minus half equals to 0. So just check the indices, they make sense. Yes. Okay, so now there's a bunch of halves that we can get rid of. So there's a half here, there's a half here, and there's a half here. Okay. So over here, let's bring this term to the right hand side. Let's bring this term to the right hand side, and let's bring the rest to the left. The reason is because this term over here is actually the metric, usually alpha beta. So it's like I think it's the background metric. Yeah, I believe it's the background metric. So h is the induced metric. So this is the background metric of our ambient space in a sense. So let's isolate that term. How do we do that? We can do so by writing bringing all terms to one side. So we have tp over 2 beta and just to clarify, what is this dot product over here? This dot product is actually is a contraction of indices like that. Okay. Oh, sorry. This is not a this is the induced metric. It's not a background metric. The H is the background matrix. This is the induced metric from H alpha beta. Yeah, that makes more sense because we're taking derivatives of this object, of the P-Brane. Okay, so from here, um, we can express. Okay, we want to the goal over here is to isolate this term. So how do we get rid of this guy? We take the we can contract it with H alpha beta. So let's contract with H alpha beta, contract the indices. So TP over 2. This guy will then be he'll be it'll be the number of dimensions, which is p plus 1, right? So this is because H alpha beta is equals to the dimensions, and then from here we write the rest. They are so now this is an equation where there's no longer any free indices. All of them are summation over. And over here, what happens when we do the contraction? Okay, we'll write it like that first. Okay, so we want to ultimately substitute. We want the okay. So right now there's something quite appealing, which is that this guy and this guy is similar, so we can actually bring them to the same side, and we get that TP over 2 P minus 1, right, equal H alpha beta okay. So this is pretty nice, right? So remember previously we had the result that previously we had the equation of motion for H. So we want to substitute it back in, because now we observe that TP over 2, so we had the equation of motion, which was which one should we use? Okay, we should use this one. So this was the equation of motion, and we now have this guy, which is similar to this guy in terms of scalars only. So yeah, so we can essentially substitute it back in, and so let's first bring it to some nice terms first. So we package it nicely before injecting it inside. So this is p plus 1 over p minus 1. Okay, so we are ready to throw it in. So we substitute the pink, we substitute 1 into 2, and now we have gotten rid of this thing, so that is great. So let me just box this up for more clarity. So we go inside, So h alpha beta lambda p plus 1 over p minus 1 minus lambda p h alpha beta equals to tp. Great. So now we on the right hand side the we have the induced metric g alpha beta tpg alpha beta, and on the left hand side we no longer have all the derivatives contracted with the h alpha beta. Now everything is in terms of the induced metric. So we just need to see that this minus that is going to be 2. So is this 2 over p minus 1 h alpha beta, and that's wonderful. Okay, so where do we go from here? Okay, so from here we are almost ready to substitute it back into the Nambu-Goto action. So before that, let's take a square root and then trace on both determinant and then square root. So we take the determinant and then we take the minus determinant of square root. So yeah, so okay, before that, let me just bring the TP over to one side. So this is just going to be lambda over TP. Let me just square bracket this thing. And now we take the minus the determinant. So the determinant depends on the dimension. So determinant of a scalar times a matrix is going to be a to the number of dimensions a, or rather determinant a. So we take the determinant with respect to the alpha and betas. So we can think of alpha and betas as a matrix, and the h, so the h and the g is sort of like a matrix. And then we get that this 2 over p minus 1, this thing to the power of the dimensions, which is p plus 1, and then we take the square root, so that's p plus 1 over 2, and then minus determinant of h equals to square root minus determinant of g. So this is where h equals to determinant of h alpha beta and g is equal to determinant of g alpha beta. This is just to remind you. Okay, so wonderful. Now we have this equation. We are almost ready to substitute it in. So remember, so recall we call the Polyakov action, which is which I'm going to write down. You can refer back to the beginning of the page. Okay, so we call the Polyakov action and the Nambu-Goto action, which I will mention later. Okay, so yeah, so let's go ahead and substitute it in. So we can see that this goes nicely in here and here, right? Yeah, so wait, let me just double check. So yes, that goes in there, and then additionally there's another thing that we can substitute. So that gets rid of the square root minus h, but how about this guy? So this guy, it comes from something we wrote a bit further behind. Where might that be? This comes from here. So this comes from here. So we're going to substitute those two things inside, and what will we get? So I previously I did not write it, so but if we substitute those two things inside, then the first term is going to be, okay, the first one is then square root minus g, and then tp over, we need to invert one over, take the reciprocal, so p minus 1 over 2 and then we substitute that guy in, so there will be lambda p over tp 2p plus 1 over p minus 1. Okay, and we see that and we see, okay, and then there's, wait, we just do the second term first, so that would be tp over lambda p minus 1 over 2 p plus 1 over 2. Okay, so just to clarify, this green one is the green one over there, and the yellow terms are then oh, I forgot the determinant over here, so the yellow ones are then this. Okay, so this is ripe for simplification, so let's go ahead and simplify all that we can. So the first term is going to be this, and then we see that this is simply this guy is simply bring this in, sorry, so bring this in, that would be the guy minus 1, so there's a okay, so I'll just bring this in, the factor of tp, the guy minus 1, so tp over lambda p minus 1 over 2 p minus 1 over 2, because this minus 1 merges with this guy, and then there's a factor of p plus 1, so p plus 1, and then we add okay, and then there's the square root minus g, right, of course there's that, and then we add this guy, the second term, all within the integral, so this guy will be tp over lambda p minus 1 over 2 p plus 1 over 2, and then square root minus g. So oops, it appears we have come to the end of the page. Okay, so I suppose I will take a screenshot of this equation, and then I'll blow it up. Okay, so I'll bring this there, and I'll go to the next page. Okay, so let's continue writing it. So from the previous part, we have this, and then there's a p plus 1 okay, so let me just this, right, there's a tp okay, and then we add on this guy, tp over 2 p plus 1 over 2, and then there's p minus 1 over lambda p plus 1 over 2, and then there's square root g. So this square root g, let's just put brackets around this entire thing, and then we have square root g, square root minus g. So okay, so now, okay, I think I need to do further simplifications, but we are very close now. Just need to observe some simplifications. So clearly this guy and this guy, it mixes well, so there's a minus, right, minus 1 times, okay, I'll just write the square root minus g outside, and then this guy is tp over 2, so minus tp over 2 p plus 1 over 2 p minus 1 over 2 p p okay, actually I think I shall not do that. I should leave the one factor of tp over 2 outside and leave this as minus 1, and then this guy with so I'm just copying this over, and then after that I have a p plus 1, and then from here I have a plus lambda p tp over 2, and then this is tp over 2 p minus 1 over 2, and this is p minus 1 oh, I'm terribly sorry, this is lambda p, this is lambda p over lambda p. Oh, I did not finish this up. This is p plus 1 over minus 1 over 2, this is p plus 1 over 2. But let's go ahead and this p plus 1 over 2, yeah, that's right, so it's this entire thing, but let's go ahead and split this one into p minus 1 over 2 and an additional factor of p minus 1 over lambda p. So why do we do that? That's because this lambda p and this lambda p cancels, and from here from here we can group things up. So this is p tau v squared minus g, this is tp over 2 p minus 1 over lambda p, this is whole thing p minus 1 over 2, and then there is so this is the common term I'm factorizing out now. I'm factorizing this guy out, and then there's this guy minus this guy, so there will be p plus 1 over 2 minus there will be minus p, there will be minus p plus 1 over 2 plus p minus 1 over 2 tp. Okay, wonderful. So right now we have tp factorizes out, right? So this guy, and then okay, because besides tp there's also more factors, so there's tp over lambda p, p minus 1 over 2, p minus 1 over 2, and then there's also minus p plus 1 over 2. This actually gives you minus 1, so there's a minus sign there, and last of all there's a square root minus g over here, and wonderful. So sorry if you have been confused for the past 10 minutes, but essentially I have been trying to factorize out into this form. So what do we observe here? So we recall the Nambu-Goto action, which says that Nambu-Goto equals to minus tp integral dp tau minus square root determinant and this thing is essentially square root minus g. So so we just need to make sure So so then we know that since in order for the Polyakov and Nambu-Goto to match, this thing, right, must be equals to 1, because we want this guy equals to this guy, and they are only equivalent if this guy is equals to 1. So we then have Tp over lambda p minus 1 over 2 equals to 1, and that means that lambda p, the cosmological constant, lambda p must be equals to p minus 1 over 2 Tp. And this, my friend, is how we have arrived at the answer for the cosmological constant. So in summary, let's go back and review the math that we have done. So we want to show from the beginning, to summarize, from the beginning we wanted to show that the Polyakov action for the P-Brane is equivalent to the Nambu-Goto action, provided that we choose a correct cosmological constant appropriately. And so in order to do so, we first find the dynamics of the intrinsic metric H, and to do so we use calculus of variations, and we varied the action with respect to the metric H, and we arrived at the pink equation, which is the equation of motion for the metric. So after arriving at the equation of motion, we then proceeded to contract indices with the metric in order to find the cosmological constant and express it in terms of the other in terms of this term. And then from there we substituted it back into the equation of motion in order to obtain this equation. And from here, because we have on the right hand side of the induced metric, and we know that the Nambu-Goto action involves the induced metric, then we can take the determinant, and then from there, now from here we substitute this back into the Polyakov action, as well as another term that we got previously. And all in all, from here we essentially solve the question, but it just follows a bunch of manipulation to make sure that the things match up and is equivalent to the Nambu-Goto action. And in order for that to equal, we need to set this condition, and this condition determines the cosmological constant in terms of this parameter Tp, which I believe is the tension. So yeah, all in all, we have solved the question, and so I hope you have had a nice experience solving this question. This is my first string theory video, so I'm a little excited, but still a little uncertain about, of course I'm not an expert in string theory, so if you like this video, please leave a like and subscribe and leave a comment, because those really make my day. So if not, have a nice day. Happy physicsing. Bye.